Hello students, hope all of you are fine. Today I will discuss a numerical problem on transmission line. So here is the problem. A 30-meter long transmission line is terminated by a load impedance of 30 plus j20 ohm and the frequency is 10 megahertz. Find the input impedance at the midpoint of the line. Given that L inductance is 100 nanohenry per meter and C is the 20 picofarad per meter. So you are asked to calculate the input impedance. So I hope you know the formula for this input impedance. You can see any book or you can see in the starting material which I have already shared in the Google Classroom or in a group. Okay, remember one thing, this L and this capacitance and the inductance, and there are other two parameters you know, this R and G. R is the resistance, G is the conductance, L is the inductance, C is the capacitance. Remember this, all these four parameters will be calculated per meter. Okay, I have already explained that in the class. Okay, so that is why this unit is like this, per meter. This is also per meter. So basically this is the length of the transmission line, 30 meter, frequency is 10 megahertz, and this is your load impedance. Load impedance means, how do you write load impedance? It is basically ZL. ZL. Okay, this is ZL. And you are asked to calculate the input impedance at the midpoint of the line. Midpoint means if my transmission line length is 30 meter, midpoint means at 15, right? 30 by 2, 15. So midpoint means you need to calculate at at 15 meter. Okay, so I will, this is the formula for the characteristic impedance, you know that, and this is the general formula for R plus j omega L, G plus j omega C. This is the formula, and beta, this is the phase constant given by omega root LC. You can see this these expressions in any book. Okay, and this is the basically the formula for the input impedance. Okay, so this is basically what I've drawn a transmission line. This is a two-way conductor, you can say. I have applied a signal. This is a signal you are applying. I finished the signal. This is the load end, and this point, let us say this is Z equal to 0, and from here we are calculating the length, and this is the input impedance which we are trying to calculate. Basically, we need to calculate this Z in at the midpoint of this line. Okay. One thing remember that this L, what he was showing this, I will explain it. Okay, I will explain this later. What is this L? How do you tackle this L? Okay. One thing. This is the end which you are applying, in which you are applying the signal. So this is the generator end, this is the load end. This, I hope this is known to you. Remember one thing, I missed a point here, a 30 meter long lossless transmission line. So this is the problem, lossless. So as you know, for lossless transmission line, this R and this G, that is the resistance and G, both will be how much? 0. That means there is no loss in the transmission line. This to basically gives some voltage drop or the leakage current. Leakage current will be leakage current in the dielectric between these two conductors basically. So this I explained in the class. What is R? What is G? What is L? What is C? So basically, if you are asked to if the transmission is lossless, that means this lossless parameters. This is the loss. This actually includes the loss terms, means loss, what can you say, the losses in this transmission line. Okay, so that means if there is no loss, that means this R and G both will be 0. Okay, so if you feel any problem, you can see this, what is this R, what is this G in any book, what is the meaning of R and G and how this is coming into the picture. Remember, these are not physical parameters. Okay, these are not physical parameters, this is basically comes from the distributed elements, what you say, distributed. Okay, means there are some phenomena which we are just trying to model Okay, trying to capture here. Okay. So basically for lossless transmission line, R equal to 0, G is also equal to 0. So that means this will be 0, this will be 0. So, and this will be j omega will cancel out. So this will be basically root L by C. Okay. So L is this, C is this. Okay. Remember one thing, if they say there is no law, then if this term is not there in the question, that means they have to give this R and G. Because for a normal transmission line, for a lossy transmission line, this R and G should be there. Okay, but here our question is lossless. So this R and G will be 0. Okay, and this is the phase constant omega root LC. LC is given, omega is how much? Omega new, what is omega? Omega is nothing but 2 pi f. So f is how much? 10 megahertz. So 10 into 10 to the power 6. And it's 2 pi. Then you will get beta. This is the phase constant. Okay. So see here, to calculate the input impedance, we need this Z0. So I can calculate from here. ZL is given here, already 30 plus J20. And we need this beta L. Beta we can calculate from here. And how do you calculate this L? L will be how much? It will be 15 because we are asked to calculate the midpoint of the line. So L will be 15. Now remember one thing. Just listen carefully. If you are asked to calculate, suppose, say 17 meter from the load end. If they ask you to calculate the input impedance, the distance, say 17 meter from the load end. Okay, load end means from this. Then what you need to do, you can replace this L simply by 17. Just simply write 17. Okay, remember this distance is calculated from the load end. But if they ask you the same thing, means in a different way, say you are asked to calculate this input impedance, suppose at 17 meter from the generator end. From the generator end. If they ask you like this, then what you need to do, this L will be how much? 30 minus 17. Okay, if they ask you from the generator end, and this is from the load end. Remember this. Okay, so you need to focus on this this thing very carefully. Okay, so this they asked for this case 17 meter from the generator end. Okay, that means from here you are going 17 meter. Okay, then what you need to do, this is the total length, you need to subtract this, then you can calculate from this for this part. 30 minus 17, fine. But if they ask you that 17 meter from the load end, then just directly put 17. Okay, so this is one thing you need to remember. That means this is this length is basically being calculated from the load end. So if you are asked to calculate the input impedance at any point on the line, just see the distance from where it is mentioned in the question, from the load end or from the generator end. If they ask you from the load end, then simply write 17. Suppose they can say 18, 20, anything. It can be anything. Okay. Or if they ask you that 17 from the generator end, that means you need to subtract this 30. 30 means this is basically the length of the transmission line. So what you can say is basically this L, what you are seeing, is basically nothing but L minus Z. Z is this 17, this is the length of the line. You can write like this. So in some book they will write L minus Z. Okay, so remember this Z, this distance is from the generator end. Okay, but if they directly say that calculate from the load end, then simply you need not to worry about anything. simply write 70. Okay, so this thing I hope it is clear. If you have any problem, then you can just pause this video or rewind this video and see. Okay. So now you will be calculating this input impedance. So first of all, let us calculate this Z0. What will be this Z0? And then we can calculate this phase constant. Then I can calculate this in ZD. Okay. So I hope you can calculate from here. First of all, Z0 will be how much? Root over of LC. So L is how much? 100 nanoampere, 100 nanohenry, sorry. Nano means 10 to the power minus 9 by L. C is how much? 20 picofarad. 20 into 10 to the power minus 12. Root over of this. So if you calculate, this will be 5. Root over 5, and this will be 10 to the power minus 9 plus 12. That is 10 to the power 3. That means root over of 5 into 10 to the power 3. So this will be approximately how much? 70.71. 70.71. Okay, this you can calculate. So first you need to calculate this Z0. Then you can calculate this beta. Beta is omega root LC. Omega is 2 pi f. F means, okay, let me write it first. So 2 pi f. F is 10 megahertz. 10 into 10 to the power 6. Mega means 10 to the power 6. Root over of this L and this capacitance. L is 100 nano, so minus 9 nano Henry, and this is 20 pico, so minus 12. So this is what you have. Now if you calculate this beta will be how much? 0.08886 rad per meter. Remember the unit beta, unit is rad per meter. This is, you know, this will be ohm. So now we are ready with this. You can easily put this value in this equation. Remember, again I am writing for this case, you are asked to calculate from the midpoint of the line. Midpoint means whether from the generator end or load end, that doesn't matter. Okay, because we are calculating the midpoint. So you can directly write 15. Okay, directly write 15. Either you can directly write 15 or you can write 30 minus 15. That will be also 15. Right? So bit L will be 15. So L will be 30 by 2. Since you need to calculate for the midpoint of the line, so this is 50. Okay, or you can write like this 30 minus 50. Because it is not mentioned whether from the load end or the generator end. Because it is immaterial here. We need to calculate the midpoint. So now you can put this value and you can calculate this ZD. So if you put this ZD will be how much? 30.41 plus J 21.49 ohm. This is your answer. Okay. Z0 will be this 70.71. ZL will be 30 plus J20 plus again Z0, it means that is 70.71 tan beta L. Beta means 0.08886 into L. L is how much? 50. Similarly for this you can Z0 is this one, same thing, and ZL, this ZL is basically your this 30 plus J20, and similarly beta L. So this will be the answer. This is the procedure. This is a very easy problem. One thing I need to mention here, one is this unit per meter. Another thing is for lossless transmission line, R equal to 0, G equal to 0, because G captures the leakage current and this gives a drop across the line. So for lossless, these two parameters will be 0, because for lossy, this will have some finite value. Okay. And another thing, this L, this is why I am discussing this L. Okay. So see whether it is from receiving end or from the generator end. Okay, if it is from the load end, simply write whatever given in the question, that is what is the distance given. Say, as I take the example of 17, you can take anything. Say 17 from the load end, then simply put 17. If they ask you 17 from the generator end, 17 meter from the generator end, then what you need to do, total length, that is in this case 30, 30 minus 17, that means 13. Okay, so this, for this points you need to remember, that is why I have discussed this problem. This you can calculate easily, this is not a big deal. Okay, I hope you have understood. If you have any problem, you can ask me anytime. Okay. Problem: a lossless transmission line having Z not equal to 75 ohm, that is the characteristic impedance, has a VSWR of 3. The first voltage minima occurs at a distance 20 centimeter from the receiving end. Receiving end means from the load end, you can say, from the load end. Find the load impedance, this is ZL, given that the frequency of operation is 150 megahertz. Okay, so you need to calculate this ZL. Just remember the condition for this voltage maxima and voltage minima. What is that? See, the condition for voltage maxima will be 2 beta x max, x is of course the distance, minus theta is equal to 2n pi. And for voltage minima, this is 2 beta x min minus theta is equal to 2n plus 1 pi. Now, how do you get these two conditions? This I will discuss separately. For the time being, just remember this are the two conditions you need to remember. Okay, that means to get a voltage maxima at the point of the transmission line, to be specific, from the load end, you can say. So this x max, this x is basically here the distance from the load end. This you need to remember. That means this distance is from the load end. Okay, and since we are talking about maxima, so this is max. This is minima, so this is minima. Okay, so this x is basically the distance from the load end. You need to remember this. And sometimes remember one thing, sometimes you will see in somewhere you will see beta L, as you see from the, as you can see, as you have seen in the characteristic input impedance expression, tan beta L. What is that beta L? Beta L is, you can say, the electrical length. Electrical length. Beta is, you can say, the formula is 2 pi by lambda, the wavelength, and the L. Okay. So like that, beta distance. This beta you need to multiply with distance with beta, then you will get an electrical length. Okay. And this theta, I am coming to that. What is this theta? It is basically from the angle associated with the reflection coefficient. Okay, reflection coefficient basically gives that how much your wave is reflected back from the load end to the generator end. Okay, from generator, that means you are applying a signal. From generator to load, this is, you can, this we generally say forward direction. Generator to load, and from load to again this generator, then we see the reflected wave. Okay, so one is the forward direction, one is the backward direction. That means source to destination, destination to source. Okay, and this is 2n pi, where n is your the values are 0, 1, 2, 3, like that, integer. So here you see the fast voltage minima. So fast voltage minima means we need to concentrate on this one, the second one, because we have voltage minima condition in this part. The fast voltage, this fast, what is this fast means? Fast means this n. What will be the value of n? What will be the value of n? The fast means, remember, that means the fast value of small n. What is the fast value of small n? That means fast voltage minima corresponding to fast value of n. What is the first value of n? That is 0. Okay. So that means for first voltage minima, this n is 0. That means basically this will be 2 into 0 plus 1 pi. That means basically pi. For first voltage minima, okay, we are putting the first value of n. Say if they ask the second voltage minima, if they say, suppose, then your n should be this 1. It was the second value of n. Okay, like that way. If this is a third voltage minima, then this 2, like this one. Fine. So basically we need to consider on this. Beta is how much? Beta it is not given, we need to calculate. X mean is given, X mean is 20 centimeter. And theta we need to calculate. Theta we will be getting from, I told you, it is the angle associated with the reflection coefficient. So you need to calculate the reflection coefficient first. Then you get this theta. And this beta is basically easy. Beta, how much? Beta, what is the formula for beta? 2 pi by lambda. 2 pi by lambda. So 2 pi is, you get a value, and lambda we need to calculate. So let us see what is the value of lambda first. So first is, we need to calculate the value of lambda. So this is 150 megahertz. That means 10 to the power 6. And what is this value of this velocity? You can consider the velocity of light. Velocity of light. What is the velocity of light? 3 into 10 to the power 8. Okay. This is velocity of light. J we write it as small c. Okay. This you can also calculate. Means 1 by root mu naught epsilon. Mu is 4 pi into the minus 7, and this is the permeability, this is the permittivity. Permittivity is how much? 8.854 10 to the minus 12. So from there you will get this value. Okay, it is for free space I am talking about. So this basically is the velocity you can consider, because it is not given anything here. But not the dielectric constant is also not given. So we can consider the simply here the free space. Okay, so this will come out as 2 meter. This wavelength will come out as 2 meter. Okay. Now what will be our next job? To calculate beta. What is beta? Beta is 2 pi by lambda. So 2 pi by lambda means 2 pi by 2. It is pi. Okay. This is your beta. Now let us put this in this condition. So what we have? 2 beta. Beta is how much? Pi. X mean is how much? 20 centimeter. 20 centimeter means 0.2 meter. Right? So let us write 0.2. Minus theta. Theta you need to calculate, and this is equal to pi. So this is what we have. So basically from this condition what we are calculating is theta. What will be my theta? Okay, so theta will be basically, this will be 0.4, this will come out, so this will be minus 0.6 pi, or if you directly change this to degree, how much? Minus 108. You know how to calculate from degree radiation, degree radian conversion, you know. So right, put 180 degree, you can get. It's 180 degree basically pi. So pi 180 degree by pi will cancel out. So 180 degree. So this conversion you can do. Okay, so this is your angle theta, and this, what is this angle? This is associated with the reflection coefficient. Now reflection coefficient, we know this much of formula. So those who are have already studied this transition line, means control theory part, this formula expressions like that, I will recommend they can go through this problem. Those who are not yet started, please don't go through this problem first, because this will be it will be little difficult for you to pick up. Okay, so first of all goes to the theory part, all the derivations part, and what are these parameters. Then you come with this, then try to solve this problem. It will be easier, of course. Okay, so the reflection coefficient at the load end, L for load, at the load end is basically given by ZL by Z0 by ZL plus Z0. What is this load end? This is the load impedance. This is the characteristic impedance. So Z0, see here it is given 75. ZL we need to calculate. Find ZL. So this you need to calculate. Okay. Another formula for the reflection coefficient is S minus 1, S plus 1. What is S? S is basically your VSWR. This is VSWR. Voltage standing wave ratio. You can denote it by S, small s. So basically the VSWR formula, you know this. VSWR is equal to 1 plus mod value of the reflection coefficient at the load end by 1 minus nt. Okay, from here you can write this, that your gamma L will be S minus 1 by S plus 1. Of course the magnitude. Okay, so what we can do here is basically we can calculate this reflection coefficient first. Okay, how do you calculate this reflection coefficient? Let us take the help of this equation. So gamma L is equal to S minus 1, S plus 1. See, S is VSWR. VSWR is how much? VSWR is 3. So 3 minus 1, 3 plus 1. So how much? 2 plus 4, that is 1 by 2, that is 0.5. So this is the reflection coefficient. This is the magnitude part, magnitude value. Now, this theta is this minus 108, and this mod value is 0.5. Okay, you can take the mod. Now we know this formula. So what you can do is, let us take this part, this much. What is that? ZL minus Z0 is equal to ZL by ZL plus Z0 is equal to, what is the mod value of gamma L? It is 0.5. So 0.5 into e to the power multiplied by j theta. What is theta? Theta is minus 108 degree. Okay, and of course this Z0 is basically 75. Now I think you can calculate this. So what you can do, you can calculate this ZL from here. Okay, so e to the power j theta, you know, what is that? Cos theta plus j theta, j sin theta, right? So you are asked, the angle is J108. So that means cos 180 degree minus the cos part, cos minus theta is basically cos theta. So there will be no minus here, and this will be minus j sin 108. This minus because sin minus theta is sin minus sin theta. Okay, that means I am talking sin minus theta is minus sin theta. Okay, that is why it is minus. Okay, so let me wrap this part. What we have, if you are unable to see this, I am writing once again. E to the power j theta is basically cos theta plus j sin theta, and we have theta as minus 108. So minus j108 degree. So cos minus 180 degree plus j sin minus 180 degree. So this will be basically cos 180 degree minus, this will be minus, this will be basically minus j sin 180 degree. Okay, now you can calculate what will be this value. Okay, so now you can calculate, put this value in this equation. Now you can calculate this ZL. What will be this ZL? ZL will be how much? 98 ohm. This will be your answer. Okay, so put this value in this equation. ZL minus Z0 by ZL plus Z0 equal to this. So this you can calculate from here, and other parameters are already given. I hope you can calculate this ZL. Okay, so the thing is, one thing that this formula, this X what we have put is basically calculated for the load end. So basically, if this is my load end, say this is the voltage axis, this is the length. So electrical length you can say beta L. So voltage minima means minima is this, the minimum voltage. Voltage maximum means this one, voltage maximum. Okay. So here it is a fast voltage minima occurs at 20 centimeter. That means from the load end 20 centimeter. This is this value 20 centimeter. Okay. So I will explain that how the condition that will come out, that what we have used here. Okay, I will derive that. Okay, but remember one thing, that reflection coefficient, you can have magnitude part as well as an angle part, and this one is basically the magnitude part. You can take the help of this Vswr equation, and wavelength beta v by f, velocity by frequency, this is known to you, and beta is 2 pi by lambda. So this is you can calculate. Okay, and we are taking the velocity of light, 3 into 10 to the power 8. This is basically calculated from this 1 by root over mu naught epsilon naught. Okay, I hope this is clear. Okay, this is a very important problem for your examination purpose. So remember, what is the voltage minimum? Another thing, just remember input impedance maxima, input impedance minima. That is the maximum value of input impedance and minimum value of input impedance. The formula is very simple. Formula say Z in max. If you say, then how do you calculate Z? Impedance, voltage by current. So voltage here, if I say max, that means Vmax by current will be minimum, of course. So this is the formula for Vmax by min. And for minimum, this will be Vmin by Imax. And remember one thing, this S, this Vswr is nothing but the ratio of Vmax by Vmin, or Imax by Imin, or Imax by Imin. This is known to you. You can see in the book. From there, you can write that this Z max will be S Z0, and this will be Z0 by S. This formula you should remember. That is the minimum value of input impedance, maximum value of input impedance. Nothing but Vswr into Z0, and this is Z0 by S for the minimum case, for the minimum case. Okay, this you will find in the book. Okay, I have discussed because these two are also important formula. Okay, there are some formulas like this also in what is the maximum voltage, what is the minimum voltage. All the formula you should remember. Okay, I hope you have understood. Thank you very much.